Okay, so we have an ideal transformation circuit. So we have to find the source current, output voltage, and complex power supplied by the source. So first thing, we have this chart here to help us determine uh, the sign of our turning ratio. So pretty much our turning ratio is V2 over V1, which is equal to I1 over I2, which is equal to N2 over N1, which is equal to N. Okay, so this N is our turning ratio or turn ratio. So instead of having a mutual inductance value, we have our turn ratio to compensate for that. And depending on the position of the dot and our current directions, our turning ratio may be negative or positive, as you see in this chart here. So solving this circuit is a little weird. Like I find solving this kind of circuit weird. So what we do is we do a Thevenin circuit from these two terminals, where we look at it from here. So we're pretty much going to ignore this and ignore this whole region and read out the circuit like this. So this is V1. We have I1 here. Then we have V2. VO here. And 20 ohms up here. So, okay, so first thing, let's find V Thevenin, which will pretty much just be equal to V1. The next thing we see is I1 should be 0 because this is an open circuit, and then there's I2 here, and there's no mutual inductance if I1 is 0. So that means I2 should also be 0, which means V2 will be equal to VO. Okay, so that's pretty much the first part done. Next part we're going to do is Thevenin impedance. Okay, so adding a test charge here. Don't worry about what the value is, but it's the Thevenin impedance should be V1 over I1. So ZTH would be V1 over I1. Now, we know that the following is true. We know V2 over V1 is equal to N, and we know I1 over I2 is also equal to N. So that means V2 over N is V1, and I1 is equal to I2 times N. So we can plug those into our formula here. Z Thevenin is V2 over N all over I2 over N. Sorry, I2 times N. And this is pretty much just V2 over I2 times 1 over N squared. And this value, V2 over I2, that's pretty much referring to this region, because recall V2 is equal to VO, and I2 is the current passing through this resistor. So this will just be Z2. And we know what Z2 is because we're told it's 20 ohms. So this is 20 ohms, and we can also find N2 because recall N1 is pretty much this region. So N1 is 1 and N2 is the right region. So it's that. So N will be pretty much 2 over 1. So it's just 2. So it's 2 squared. And that's 5. And now we have Thevenin resistance, or I'm sorry, impedance. Now we can find I1 and our output voltage. So this is how we're going to start. We are going to first draw the Thevenin circuit. So obviously it's the load we removed. So 4 ohms here and minus 6 j ohms, because remember, this part of the circuit we removed, so we included in our Thevenin circuit. Okay, and now we include our Thevenin values. So we have a Thevenin resistance of 5 ohms. Then we also have a Thevenin, we are looking for a Thevenin voltage. Okay, so this one is supposed to be V1, because we see V Thevenin is equal to V1, but we know V1 is also equal to V2 over N. Okay, so this is how we're gonna find everything out. To find our current I1, what we can do is if we can ignore this portion and then solve for I1. So it's pretty much going to be minus 120 phasor 0 plus 4 minus 6j plus 5 I1. And then just bring this to the other side. I1 will be 120 phasor 0, 9 minus 6j. And let me see what that's in phasor format. So 10.816 phasor minus 33.69 degrees. So that's just 11.094 phasor 33.69. Okay, now we can use that information to find I2 and then use that information to find VO. So recall I1 over I2 is equal to N. But before we use this, we have to check this chart here. So we look for the circuit that matches this region and the directions of current. So we see this current is moving into here, and this one's moving out from here. This one and this one are a match, but we see the position of the dots are in opposite of each other. So we're working with this one. Okay, so that means I2 over I1 will be equal to I1 over I2 is equal to N. Okay, but oh yeah, the charge, so I2 equals I1. I2 over I1 is equal to 1 over N. Okay, so I1 over I2 is equal to N. But in this case, it's minus N. So we know what I1 is. We need to find I2. So it's minus 11.094 phasor 33.69 all over N, which we calculated to be 2. So we would get minus 5.547 phasor 33.69. Bring the minus into our phasor, so we'll add 180, which is 213.69 degrees, and that's my I2. And now we can find VO. VO will be 20 times I2. So it's going to be 20 times that value, which is 110.94 phasor, 213.69 degrees, and in ampere. Sorry, in volt. Now our last part is to find the complex power. So complex power is equal to Vrms times Irms, the conjugate of I. So pretty much whatever phasor value we have, we take the negative of it. So Vrms, it's going to be, so for pretty much finding the complex power supplied by the source is this value, and we're timesing it by the conjugate of I1. So it's 120 phasor 0 degrees, and I1 was 11.094 phasor 33.69 degrees, and this pretty much means to flip the sign for this. So it's 1331.28 phasor minus 33.69 watts.